In the last talk, we established that every clinical encounter starts with a pretest probability, your best estimate of disease likelihood based on prevalence, signalment, history, and physical exam. Now comes the question, what do you do when new information arrives? What happens to that probability when a test comes back positive or negative? The answer is Bayesian updating. And despite the intimidating name, the core idea is something you already do instinctively. This talk is about making it explicit, rigorous, and teachable. We're also going to build our first 2x2 table together, the single most useful tool in diagnostic epidemiology. By the end of this talk, you'll be able to construct one from scratch and use it to calculate how a test result changes your probability estimate. The key insight here is that probability is not a fixed number. It's a moving target that updates every time new information comes in. We call the starting estimate the pretest probability. After we receive new information, a test result, a response to treatment, a second opinion, we revise that estimate. The revised estimate is the post-test probability. The term Bayesian comes from Thomas Bayes, an 18th century statistician. But don't let the name intimidate you. The concept is intuitive. If you think there's a 70% chance your patient has disease X, and then the test for disease X comes back positive, your probability should go up. If the test comes back negative, it should go down. How much it goes up or down depends on how good the test is, and that's what we'll quantify. Importantly, Bayesian updating isn't just for lab tests. It applies every time you get new information. A therapeutic trial is Bayesian updating. A follow-up exam is Bayesian updating. A call from the referring vet with additional history is Bayesian updating. This is the engine of clinical reasoning. Before we can talk about Bayesian updating in any quantitative way, we need a tool to organize the information. That tool is the 2x2 table, also called a contingency table, and it is the single most important table in all of diagnostic epidemiology. I want you to be able to draw this from memory. Here's how to read it. The rows represent what the test says, positive or negative. The columns represent what's actually true, disease present or disease absent. Notice that what the test says and what's actually true are two different things. That gap between them is where all the interesting and clinically important stuff happens. The four cells are true positive, the test said positive, and the disease is actually there. That's a correct positive. True negative, the test said negative and the disease is truly absent. Correct negative. False positive, the test said positive, but there's no disease. This is a false alarm. And false negative, the test said negative, but the disease is actually present. This is a miss. The colors I've used here are intentional. Green for correct results, red for a false positive alarm, orange for a false negative miss. We'll come back to why the colors differ between those two error types, because the consequences of false positives and false negatives are very different, and context determines which is worse. Let's build one together. This is the most important skill in this talk, being able to construct and populate a 2x2 table from scratch. I'm going to walk you through it step by step. Our scenario, we're testing 1,000 cats in a heartworm endemic region. The true prevalence of feline heartworm disease is 5%, meaning 50 of our 1,000 cats actually have heartworm, and 950 do not. Our antigen test has a sensitivity of 80% and a specificity of 95%. We'll define those terms fully in the next talk. For now, just know that sensitivity tells us how often the test correctly identifies a sick animal, and specificity tells us how often it correctly identifies a healthy one. Step 1. Fill in the column totals. Disease present equals 50. Disease absent equals 950. Step 2. Use sensitivity. Sensitivity is 80%, and there are 50 truly infected cats. So the test correctly identifies 80% of 50 equals 40 cats. Those are our true positives. The remaining 10 infected cats test negative. Those are our false negatives. Step 3, use specificity. Specificity is 95%, and there are 950 truly uninfected cats. So the test correctly identifies 95% of 950 equals 902.5. Let's round to 903. Those are our true negatives. The remaining 47 uninfected cats test positive. Those are our false positives. Step 4, check your math. True positives plus false negatives should equal 50. 40 plus 10 equals 50. Check. True negative plus false positive should equal 950. 903 plus 47 equals 950. Check. Now we have a complete 2x2 table and can answer some very important questions. Here's the completed table. Take a moment to look at those numbers. We ran 87 positive tests total, but only 40 of those positives are true positives, cats that actually have heartworm. The other 47 are false positives, cats that tested positive but don't have heartworm. That means in this population, with this prevalence, over half of all positive results are false alarms. Let that sink in. The test hasn't changed. Its sensitivity and specificity are fixed. What changed is the prevalence, the starting probability. When prevalence is low, even a pretty good test generates a lot of false positives. This is Bayesian updating in action. When you get a positive result on a low prevalence disease, your post-test probability should not jump to near certainty. It should reflect the reality that most of those positives are false alarms. This is why a positive feline leukemia ELISA on a low-risk indoor cat should be confirmed with a second test before you give that owner life-altering news. You're updating your probability, but in a low prevalence situation, one positive result doesn't get you to certainty. We'll calculate exactly how much a test result should shift your probability using likelihood ratios and predictive values in the next two talks. For now, the key takeaway is your post-test probability depends on both the quality of the test and your starting prevalence. Before we wrap up, let me give you the intuitive summary of Bayesian updating. The rule of thumb that lets you do this reasoning quickly at the bedside, even without a table. A test result moves your probability in the direction of the result. Positive pushes it up, negative pushes it down. But where you land depends entirely on where you started. If you started with a high pretest probability and the test comes back positive, you're now very confident. The test confirmed what you already suspected. If you started with a high pretest probability and the test comes back negative, you're now only moderately less confident. A negative result on a high prevalence disease doesn't rule it out, especially if the test has imperfect sensitivity. Now flip it. Low pretest probability, positive result. You should be moderately suspicious, but not certain. Most of those positives are false alarms in a low prevalence situation. Low pretest probability, negative result. Now you can be reassured. A negative test in a low probability patient is a genuinely good rule out. This is the intuition. It's not a substitute for the math, which we'll cover in full, but it's the mental model that should be running in the background every time you look at a test result. Let's recap the key points. Bayesian updating is just the formal name for revising probability when new evidence arrives, and it's something you do every day in clinical practice. The 2x2 table is your tool for organizing this information. It has 4 cells: true positive, false negative, and true negative. You build it by starting with prevalence, your column totals, then applying sensitivity and specificity to fill in the cells. And the critical insight is that your post-test probability depends on both the test quality and your starting prevalence. When prevalence is low, even a good test will generate mostly false positives. In the next talk, we'll talk about the cognitive shortcuts and mental traps that derail this kind of careful reasoning, the biases that make us ignore base rates, anchor too hard on early information, and close our minds prematurely. Read the following problem, pause the video while you solve it. Let's work through this carefully. Step 1. Prevalence is 2%. Out of 1,000 animals, 20 truly have the disease and 980 do not. Those are your column totals. Step 2. Sensitivity is 90%. Apply it to the 20 truly diseased animals. 90% of 20 equals 18 true positives. The remaining 2 are false negatives. Step 3, specificity is 90%. Apply it to the 980 truly disease-free animals. 90% of 980 equals 882 true negatives. The remaining 98 are false positives. Step 4, check. 18 plus 2 equals 20. Check. 882 plus 98 equals 980. Check. Now for the punchline. There are 116 total positive tests, 18 true positives, and 98 false positives. So only 18 out of 116, which is about 15.5% of positive results, are actually correct. Even with a test that is 90% sensitive and 90% specific, in a 2% prevalence population, fewer than 1 in 6 positive results is a true positive. This is a result that surprises almost everyone the first time they see it. It is not a flaw in the test. It is a mathematical consequence of low prevalence. And it is exactly why you must always consider your pretest probability before acting on a test result.